Light and optical instruments. What is light? You know it helps you to see, but do you know how? Do you know what causes the shimmering colors in the northern lights? Why do we see things in color? For centuries, scientists around the world have tried to find answers to these questions. Gradually, they have developed explanations for light and color, and with their growing understanding has come an ability to use light for many technological purposes. In the past, people could obtain light energy only from fire and the sun. Today, we use laser lights, radio waves, infrared light, and other forms of light energy in many applications. During laser eye surgery, for example, powerful laser light can vaporize tissue from part of the eye to correct vision. Our ability to produce and control visible light and radiation benefits our daily lives in countless ways. In this unit, you will learn about visible light and other kinds of radiation and the many ways in which we apply them. Chapter 7, Understanding Light. Getting ready. How is the light from the light bulb similar to the light from the sun? 2. Why do you have to stand directly in front of a bathroom mirror to see your face? Why do objects look different when they are immersed in water? Think about all the ways in which you have used light during the past few days. How many times did you control the brightness of light or make a shadow? How often did you use a mirror to see reflections off a shiny surface? Do you or any in your family wear glasses to correct lenses? Perhaps you used a camera, a pair of binoculars, or other optical device. This chapter will discuss some common sources of light, both natural and artificial. It will also introduce some interesting properties of light to help you understand how light travels and how it becomes or behaves in predictive ways. Spotlight on key ideas. In this chapter, you will discover 1. How various sources produce light. 2. 2 basic properties of visible light. 3. How to use the laws of reflection to describe the behavior of light. 4. What happens to light when it strikes different types of surfaces. And 5. How transparent objects can change the path of light. Spotlight on key skills. In this chapter, you will 1. Use a protractor to measure angles of reflection and refraction. Calculate the cost efficiency of lighting. 3. Analyze experimental results using diagrams. And 4. Design your own investigation of refraction. What is light? In the simplest terms, light is the form of energy that you can see. The sun is a natural light source, the most abundant and least expensive light source in the world. Fire is another natural source of light. See Figure 7.1. Figure 7.1, besides the sun and the stars, flames and sparks are natural sources of light. The sun is a star. All stars in the universe are sources of light. Light spreads out or radiates from the sun and other stars in all directions, like the spokes of a bicycle wheel. This type of energy transfer does not require matter. It is known as radiation. Energy, such as light, that travels by radiation is often called radiant energy. Less than 1/10 of 1/millionth of a percent of the sun's energy actually reaches Earth. But our lives are totally dependent upon this energy. Plant people and other animals could not live without light from the sun. Because sunlight is not always available, people have developed light-producing technologies or artificial lights. A light bulb is an example of an artificial light source. Like the sun, light from a bulb radiates in all directions. What else can produce light? Think about what happens when you strike a match. Chemicals on the tip of a match react to produce heat and light. Once the chemical energy is used up, the match is no longer useful. Like the match, all other sources of light require energy. Flashlights use electrical energy from batteries. Light bulbs glow when you switch on electricity. The light that leaves the sun is formed through a process called nuclear fusion. Light from the sun is produced by nuclear fusion of hydrogen particles. The sun is composed of about 70% hydrogen. When hydrogen particles combine, they form another particle called helium. During this process, an enormous amount of energy is released as heat and light. The temperature inside the sun is about 16 million degrees Celsius. That's off the wall, top left page 204. We had a power failure at night, and it was very cloudy. You couldn't see your hands in front of your face. There was no light for 5, 6, 7, 8, 9, 10 miles in any direction. And it was so dark, it was unbelievable. It was like you were in a closet at night with the door shut, and inside the closet was another closet that you were inside. You saw no light. Then the next night, the sky was clear, and you could see perfectly well. For a night, you could see perfectly well because of just the starlight. Starlight is much more intense than people think it is. The first basic property of light. You've seen that light is a form of energy. This is the first basic property of light. When light is absorbed by a surface, it can be transformed into several different forms of energy. Light can be transformed into thermal energy, electrical energy, or chemical energy. For example, the absorption of sunlight by a black sweater causes the garment to gain thermal energy. Solar cells change light into electricity. Trees in your neighborhood absorb sunlight to make chemical energy, sugars. Figure 7.2. Sunlight is absorbed by the pavement on this runway and transformed into thermal energy. You can see heated air rising from the pavement on a road or a runway on a hot, sunny summer day. The brightness or intensity of light indicates how much energy a surface will receive. A surface can absorb more energy if the brightness of the light intensifies. For instance, pavement may feel hot to the touch, or a sunny summer day, see figure 7.2. However, the pavement will look only warm if the clouds block out the sunlight. In the activity below, explore further the concepts of light, intensity, and radiant energy. Sources of light. How would your life be different if the sun and stars were the only sources of light available to you? You would probably go to bed very early, especially in the winter, because there would not be much that you could do after dark. Without artificial sources of light, there would be no television, no lamps for reading, no computers. All the rooms in the building would probably have windows or skylights. We are lucky to have many sources of light available to us. In earlier times, once the sun had set, people found their way around outside with the aid of torches and lanterns. Candles and oil lamps were commonly used indoors. Imagine trying to study by the light of a candle. Today, we have so much light in our cities that light pollution can wash out our view of the skies at night. That is why many observatories, such as the one shown in Figure 7.3, are located far from urban areas. Figure 7.3. This photograph is a time exposure image of star trails over the dome of the Mayall telescope at Kitt Peak National Observatory in Arizona, USA. The telescope's high-altitude location, over 2,000 meters, and the clear desert skies reduce atmospheric interference to incoming light. However, some communities are taking steps to conserve light energy. For example, new types of street lights are designed to direct their light downward so that they illuminate the ground or the street and not the sky. In addition, these lights are comparatively energy efficient. For example, the yellow sodium vapor lights shown in Figure 7.4 on the next page are much more efficient than white lights. Figure 7.4, these bright yellow lights contain sodium vapor. Electricity makes the gas glow, producing a very intense yellow light. Incandescent sources. An object can be heated to such a high temperature that it emits visible light. Such an object is called an incandescent source of light. The emission of visible light by a hot object is called incandescence. Both candle flames and light bulbs are examples of incandescent sources. As you saw in the starting point activity in the light bulbs used most commonly in our homes, electricity heats a metal wire filament in the bulb. See Figure 7.5. This filament becomes so hot that it glows white. The change from electrical energy to visible light energy involves the following energy transformation. Electrical energy yields thermal energy, yields visible light energy. Have you ever touched an incandescent bulb right after you turned off the light? If so, you probably burned your fingers. About 95% of the energy given off by incandescent light bulbs is released as heat. In a way, an incandescent source of light is like having a small electric heater in the room. Did you know the filament in an incandescent light bulb is usually made of the element tungsten? Figure 7.5, an incandescent light bulb. Notice the filament that is oftentimes tungsten. And it gets so white hot, you're actually converting infrared energy to visible light, as opposed to fluorescent sources, which is converting ultraviolet light to visible light. So incandescent goes from infrared to visible, and fluorescent goes from UV to visible. Fluorescent sources. You may have noticed that when you stand under a so-called black light, some of your clothing glows, especially white socks. In this process, high energy invisible ultraviolet light is absorbed by the particles in the fabric. You will learn more about ultraviolet light in Chapter 9. These particles then emit some of this energy as light that you can see, making the clothing glow. This glow is called fluorescence. You can summarize this energy transformation as follows. Ultraviolet light energy yields energy absorbed by particles yields visible light energy. So you're going from ultraviolet to visible light. A fluorescent source of light makes use of this energy transformation. Figure 7.6 shows the typical parts of the fluorescent tube. An electric current from the lead-in wires and electrodes cause the mercury vapor inside the tube to give off ultraviolet radiation. The phosphor coating on the inside of the tube absorbs the ultraviolet energy. This causes the coating to glow, thus producing light that you can see. The energy pathway for a fluorescent source is summarized as follows. Electrical energy yields energy absorbed by mercury particles, yields ultraviolet light energy, yields energy absorbed by phosphor particles, yields visible light energy. 7.6, a fluorescent tube. So on either end of the bulb you have two pins, and then you have the lead-in wire, and then you have the electrode, and then you also have mercury vapor. The mercury vapor is invisible. You have the glass tube. On the inside of the glass tube, you have phosphor coating. You have regular mercury that's put into the vapor, and that's approximately it. Fluorescent tubes have a few disadvantages compared to incandescent light bulbs. They are much more expensive to manufacture and more difficult to dispose of than incandescent bulbs. Also, both the phosphor coating and the mercury vapor of fluorescent tubes are toxic. However, if you compare the energy pathways for the fluorescent tube and the incandescent light bulb, you will notice a definite advantage for fluorescent sources. Thermal energy is not involved in the operation of fluorescent light sources. You can even touch the tube when they are lit. As a result, fluorescent lighting wastes much less energy as heat than incandescent lighting. In other words, fluorescent lighting is more energy efficient. Most schools and businesses use fluorescent tubes rather than incandescent bulbs to conserve energy and thus save money. This book was written probably 20 years ago. The cost of fluorescent tubes for lighting and the new energy efficient ones for lamps, the little screw-in ones, are much less expensive than they were at the time this book was written. Phosphorescent sources. A phosphorescent source of light is similar to a fluorescent source. Light energy is absorbed by certain particles that can store this energy for a while. The stored energy is later released as visible light. The original light energy may be either in the form of high-energy ultraviolet light, as in fluorescent tubes, or in the form of visible light. The persistent emission of light following exposure to and removal of a source of radiation is known as phosphorescence. Let me read that again. The persistent emission of light following exposure to and removal of a source of radiation is known as phosphorescence. The main difference between fluorescent source and phosphorescent source is that particles in the fluorescent source release their light energy immediately. Phosphorescent particles take longer to emit light, and they continue to glow for a while after the energy source had been removed. See figure 7.7. Phosphorescent materials are often used in photographic darkrooms. This phosphorescent dial on a darkroom timer glows to indicate how long a photograph should remain in various solutions. And you can see that that is analog instead of digital. So the book is old. Chemiluminescent sources. Chemiluminescent sources. Light can also result from the energy released in chemical reactions. The chemical reaction produces particles that give off visible light energy. This process is called chemiluminescence. The energy pathway for chemiluminescent source can be represented as follows. Chemical energy yields visible light energy. Glow sticks, often used as emergency signal lights, produce light by chemiluminescence. In a glow stick, a breakable barrier releases two liquids. Bending the stick causes the barrier to break. The liquids mix and cause a chemical reaction that releases light, as shown in Figure 7.8. Figure 7.8. A mixture of chemicals releases light when a glow stick is bent. The stick will glow for several hours until the chemical energy is used up. Bioluminescent sources. If you were moving through the darkest depths of the ocean in a research submarine, you might be surprised to see glowing creatures swimming past your porthole. See Figure 7.9. 7.9. How might bioluminescence be helpful to these jellyfish? These animals cannot be incandescent or fluorescent sources. Instead, they rely on chemical reactions inside their bodies to provide the energy for light. This special type of light produced in light creatures is called bioluminescence, and the result is known as a bioluminescent source of light. Many organisms that live deep in the ocean use bioluminescence because so little sunlight reaches far below the surface. Some fish produce bioluminescence to attract prey. Certain fungi in caves also produce bioluminescence, as do fireflies. Fireflies glow to attract mates. Figure 7.7, referring back to chemiluminescence. A mixture of chemicals released light. When a glow stick is bent, the stick will glow for several hours until the chemical energy is used up. The cost of lighting. So far you have looked at how various light sources produce light. Now consider the cost of using different sources of light. Since incandescents and fluorescent sources are the most common around the house, you can compare their costs. Electrical energy costs about 8 cents per kilowatt hour. A watt is a unit of electric power. A kilowatt hour is 1,000 watts of electrical power operating for 1 hour. The symbol for watt is capital W, and the symbol for kilowatt hour is K, capital W, dot H. That's kilowatt times watts times hours. To understand how to calculate the cost of lighting, look at the following example. Example: how much will it cost to leave a 60-watt bulb on for 10 hours if electrical energy costs 8 cents per kilowatt hour? You can tell this book is old because light does not cost, or electricity does not cost 8 cents per kilowatt hour. It costs much more than that. Convert 60 watts to kilowatts by dividing by 1,000. 60 watts divided by 1,000 equals 0.06 kilowatts. Calculate the number of kilowatt hours by multiplying the power in kilowatts by the number of hours. Number of kilowatt hours equals 0.06 kilowatts times 10 hours equals 0.6 kilowatt hours. Calculate the cost of leaving the light on for 10 hours by multiplying the number of kilowatt hours by the cost per kilowatt hour. Cost in cents equals the amount of energy in kilowatt hour times the unit price in cent per kilowatt hour. Cost equals 0.6 kilowatt hours times 8 cents equals 4.8 cents. Therefore, the cost of leaving the light on for 10 hours is 4.8 cents. Now, first of all, let me just say that that's a 60-watt light bulb. So that's an incandescent light bulb. And they'll get into that in a moment. Fluorescent tubes are more energy efficient than incandescent bulbs. A fluorescent tube with a power of 12 watts can produce the same amount of light as a 60-watt incandescent bulb. The cost of operating a 12-watt fluorescent tube for 10 hours will be 0.96 cents, not even a penny. This is only 1/5 the cost of operating the 60-watt incandescent bulb for the same amount of time. The second basic property of light. Understanding the first basic property of light, that light is energy, helps explain some aspects of light. However, it does not explain everything. When someone stands in front of you during a movie, part of your view is blocked, as shown in figure 7.10. A shadow results because light travels in straight lines from its source and does not bend around objects. This hints at another basic property of light. The light from the screen will not bend around the person to reach your eyes because light travels in straight lines from its source. This is the second basic property of light. Knowledge of how light travels allows us to predict how light will behave. To show the path of light, you can draw a straight line with an arrowhead to show the direction in which light is traveling. This type of drawing is called a ray diagram. See figure 7.11. 7.11. Light will travel in straight lines until it strikes something. Until light strikes something, it will continue to travel in straight lines away from the source, as shown in figure 7.11. When light strikes clear substances such as air and water, it passes through them. These media are transparent. Window glass is transparent, and so are the lenses in your eyes. You can look through a transparent surface to see the light source clearly on the other side. Other substances let some light pass through them, but the light is scattered from its straight path. These substances are translucent. Wax paper is translucent. You can sometimes see the sources of light on the other side of a translucent surface, but the image is not clear. Many materials will not allow any light to pass through them. These materials are opaque. They block the path of light. A book is opaque, for example. As you learned in previous science studies, opaque objects produce shadows when light strikes them. 7.2, reflecting on reflections. Let's start with stretch your mind. What you see depends on the images your eyes form using the light reflected off an object, and also on your brain's interpretation of these images. Sometimes the brain misinterprets an image. Optical illusions fool our brains into making false conclusions. See figures 7.12 and 7.13. Try to create your own optical illusion. 7.12. Observe this image through one eye while you slowly lift the page up to the level of your chin. Did you see the lines on the flat page appear to rise into a gently sloping hill on the right? Figure 7.13. Study these optical illusions and answer the questions. Which auditorium has thicker columns? I will leave these to you. I'm not going to give away the answers or tell you what I think. You see some objects because they emit their own light. The sun, a glowing light bulb, and a burning candle all produce their own light energy. These objects are luminous. Most objects, however, do not produce their own light energy. They are non-luminous. They can be seen only when light from a luminous source strikes the object and then reflects off the object into your eyes. Reflection occurs when light bounces off a surface. When a room is poorly lit, you see less because less light is reflecting off the objects around you. If you shine a flashlight on an object, you can see the object clearly again because you have increased the amount of light reflecting off its surface. All the light striking an object is not reflected. Some light energy is absorbed. Dark surfaces tend to absorb most of the light that strikes them. This is why wearing dark clothes in the summer sun can make you feel hot. That is also why dark objects are more difficult to see at night. Very little light is reflected from dark surfaces, even in full daylight. On the other hand, light-colored objects reflect most of the light that strikes them. When light strikes a reflecting surface, it bounces off the surface. A light ray that strikes a surface is called an incident ray. The light that is reflected from a surface is called a reflected ray. See figure 7.14. To find out in which direction each ray of light is traveling, you can measure an angle. To do this, draw a reference line that is perpendicular 90 degrees to the reflecting surface at the point where the incident ray strikes the surface. This line is called the normal. The angle between the incident ray and the normal is called the angle of incidence. The angle between the normal and the reflected ray is called the angle of reflection. This approach provides a standard way to describe the direction in which light travels during reflection. You will investigate reflection in the next two investigations. Figure 7.14. The normal is a reference line that is drawn perpendicular to the reflecting surface at the point where an incident ray strikes a reflecting surface. The angle of incident, I, is the angle between the normal and the incident ray. The angle of reflection, R, is the angle between the normal and the reflected ray. Stretch your mind. Measure and record the dimensions of each diagram on the left to check your answers. Did any of the drawings trick your vision? Why might your brain be fooled by the drawings? Predictable behavior. Light that is reflected from a surface behaves in two predictable ways. You demonstrated this in Conduct an Investigation 7b. The two predictable behaviors of light are called the laws of reflection. The first law of reflection states that the angle of reflection is equal to the angle of incident. For example, if the angle of incident is 30 degrees, then the angle of reflection is also 30 degrees. The second law of reflection states that the incident ray, the normal, and the reflected ray are all in the same plane, an imaginary flat surface. This is why you can draw all three lines on a flat sheet of paper. Figure 7.15. The two laws of reflection. One, the angle of reflection is always equal to the angle of incidence, and two, the incident ray, the normal ray, and the reflected ray are always in the same plane. You realize that an object is in front of you only because light is spreading out from the object. As long as your eyes receive light as if it were spreading out from points on an object, you will see the object. 7:16. Only a small fraction of light reflecting from an object enters your eyes. Mirrors can trick your brain. Light is reflected off an object toward the mirror, which reflects the light back to you. The object appears to be located at the point from which the light seems to come, a position behind the mirror's surface. The image appears to be the same size and shape as the real object, and it seems to be the same distance behind the mirror's surface as the real object is in front. See figure 716 and 717. Figure 717. We know that what we see in a mirror is just an image. However, a pet bird will chatter for hours to a friend in the mirror. To confirm this, choose a point on a diagram of a reflected object and measure the perpendicular distance between that point and the reflected distance as shown in figure 7.18. Mark a point at the same distance behind the reflected surface. Do this for several other points on the object until you can see the object's shape and size emerge from the points. If you do this for enough points, you could connect the dots to draw the location and shape of the image formed by the reflection. 718. The image of an object reflected by a plane mirror appears to be at the same distance behind the mirror surface as the object itself is in front. A smooth, flat, reflecting surface always produces an image that has the same size and shape as the object. All the normals related to light reflected from a bathroom mirror point in the same direction. See figure 7.19a. Clear images are created from light reflected by a plane mirror. Compare the normals related to light reflected from a mirror to the normals related to light reflected from a wall or a piece of paper. See figure 7.19b. Although the wall and the paper surfaces might appear to be smooth, both are much rougher than the mirror surface. The normals related to light reflected from rough surfaces will point in random directions depending on exactly where the incident rays strike the surface. When light reflects off a rough surface, diffuse reflection occurs and no image results, as shown in figure 7.19b. Using reflections. Cars and bicycles have reflectors to make these vehicles visible at night. Figure 7.20. That's a bicycle reflector. Shows a reflector in which hundreds of tiny, flat, reflecting surfaces are arranged at 90 degrees to one another. These many small surfaces are packed side by side to make the reflector. When light from another vehicle hits the reflector, the light bounces off the many tiny surfaces back towards the source of the light. The driver in the other vehicle sees the reflection and realizes that something is ahead. Pool players can use the laws of reflection to improve their game. Like a light ray, a pool ball travels in a straight line until it strikes something. In a bank shot, the white cue ball bounces off a cushion because it strikes the target ball. To decide where to aim the cue ball against the cushion, the player chooses a spot that is the same distance behind the cushion as the target ball is in front. See figure 7.21. You can improve your pool game by applying the law of reflection. So you see that the target ball in red is equidistant from the cushion as is the image of the target ball. So you're actually shooting towards the image, and then that will automatically come back and reflect to the target ball. Very cool. This spot is the image of the target ball. The player now shoots the cue ball toward the image. Because the ball bounces off the cushion at the same angle at which it strikes the cushion, the cue ball bounces off the cushion and strikes the target ball. Refraction. You know that reflection occurs when light rays bounce off objects, and you can now accurately predict the direction in which reflected light rays travel by using the laws of reflection. You can also predict where an image will be located in a plane mirror. What happens when light moves from air into a medium such as water? If you have ever stood on the side of a pool and tried to dive for an object on the bottom, you may have been surprised that the object was not where you expected it to be. Refraction is the bending of light when it travels from one medium to another. Light bends because it changes speed when it moves between materials that have different densities. Light usually travels more slowly in comparatively dense material. The bending of light makes the object image appear to be in a different position from where the object really is. See figure 7.22. Explore refraction in the next two investigations. Around a bend with light. When light travels from one medium into a denser one, for example, when it moves from air into water, it will bend toward the normal. When light exits a denser substance, its direction of travel bends away from the normal. How much bending occurs depends on the type of substance through which the light travels. The new direction of the light is called the angle of refraction, R, capital R. See figure 7.23. Figure 7.23, light is refracted as it passes through one medium into a denser medium. When the angle of incidence I increases, the angle of refraction, capital R, also increases. However, doubling the angle of incidence does not mean that the angle of refraction also doubles. Refraction can also occur when light travels through air at different temperatures. Warm air is less dense than cold air. Light bends as it travels through different densities of air. The refraction of light through air can result in a mirage. Have you ever been driving along a highway on a hot summer day and noticed what looked like pools of water lying ahead? However, when you got closer to the pools, they mysteriously disappeared. You were seeing a mirage. The air close to the ground is hotter and less dense than the air higher above. As a result, light from the sky directed at the ground is bent upward as it enters the less dense air. The pools of water were actually images of the sky refracted by warm air near the ground. See figure 7.24. Figure 7.24. Refracted light is responsible for creating mirages. When air near the ground warms up, the light from objects at a distance is refracted into a curved path. This causes the illusion of water surface, which is really an image of the sky refracted by warm air near the ground. Now, before moving on to the next part, where it says is that all there is to light? Let's look very carefully at figure 7.23 and 7.24. 7.23 says light is refracted as it passes through one medium into a denser medium. So look at the normal through the object. You can see that as light is passing, so you have the incident ray in air, it hits the water, whatever it is, it's more dense. The shaded area is denser. So it's going to go toward the normal if it goes into more dense material. And then look, when it comes out of the material, you're going to see that the angle of refraction, as opposed to the first angle of refraction, is going to be away from the normal. So as it goes in, it's bent towards the normal, and as it goes back out, it's bent away from the normal. Now, don't think it always goes like that, where it's bent to it and then bent away from it. Air is not very dense relative to water. So it's going in air, and then it goes into water, bends towards the normal because water is more dense. And then when it comes out, it's bending away from the normal because it's going from water, high density, to air, low density. So it's going to bend away from the normal. And the question is that all there is to light? Table 7.1 summarizes what happens to light when it strikes different surfaces. Sometimes all three light behaviors happen at once. Light from the sun can reflect off the still surface of a lake to produce a mirror-like reflection. At the same time, the water can absorb light, transforming the light energy into thermal energy. The water warms during the day and cools off at night. If you are looking down into the water from shore, you might be uncertain about the location of the object at the bottom. This happens because light is refracted as it travels from water to air. Table 7.1, what happens when light strikes a surface? Well, one of three things is going to happen. It's going to be absorbed, it's going to be reflected, or it's going to refract. So what happens to the light striking the surface? The absorbed light changes into some other kinds of energy, and then the nature of the surface occurs mostly on rough, dark, opaque surfaces. And then what else happens? Some light is usually reflected off the object. How do you know that some light is reflected off the object? Because you can see it. I will leave the rest to you to read. Now let's go on to chapter 8. And chapter 8, we're going to look at light technologies.